So let's have a look here at a second question. This is quite a difficult question. Okay, so what it says here is that John wishes to measure the strength of a magnetic field produced by a magnet using an apparatus similar to the one shown below. And you're given all these different lengths of stuff. You've got there the mass of 0.1 grams over on the right hand side. And then here it's just a bit of a description of the diagram. So it says the beam with a 15 turn rectangular 6 by 2 centimeter coil on one end. So that's referring to this part here, is 6 by 2 centimeter rectangular coil. And there's a 0.1 gram mass added to the other end. The beam tipped up. It was brought back horizontal by passing a current of 1.7 amps through the coil. Okay, so it's saying, I'll put the mass here, it caused the entire thing to tip up a little bit. Then when I passed 1.7 amps through this coil, it brought it back down to level. Okay, so if it brought it back down to level, then I suppose what do we know at that point? It means if it's not really moving from that point, then the torques are actually equal. Okay, and that's the key to this question. It was given in the original question, it said by equating torque due to the mass with torque due to the current, solve for the strength of the external magnetic field. But I've left that part out. I left it out in my booklet just to see if students could actually see what we need to do to solve or to approach this problem. Okay, so our first thing to say, well, seeing as it's brought back horizontal, okay, and it's not shifting from that, the torque due to the mass over here and torque due to the current over there are actually going to be equal. Okay, so I might say, torque due to the current, I might call it torque I, is equal to torque due to weight. Okay, now torque due to the current. So what we have here is the torque is only acting on this side. Okay, so we're looking at our NBIL for this side multiplied by a distance of 6 centimeters. Okay, so this becomes NBIL, which is our force due to the magnetic field interacting with the current carrying conductor, times the distance, which we might just call D1, from the point about which it's rotating. And we're going to say that's equal to the torque due to the weight. Okay, so the force there is mg times d2. Okay, and basically we have everything here except the external field strength, so we can rearrange and solve for the external field strength. So let's plug in some numbers. So here we've got NBIL, so it's a 15 turn rectangular coil. So this becomes 15 times B times the current, 1.7 amps, times the length of the coil. So this is the length of the coil that's actually in the magnetic field. So that's just this 2 centimeters here, which we're told is 2 centimeters up there. So that's 0.02 times our distance. How far away is it from the point about which it's rotating? So it's rotating about here. So it's 6 centimeters away from that. So that is equal to mgd. So m is 0.1 grams. Don't forget you need to change that to kilos. So it's not just 0.1, it's actually 0.1 times 10 to the minus 3 or 1 times 10 to the minus 4. Times our 9.8 times our distance of d2, which is 0.05. Again, don't forget to always show all your working. I know it's tedious sometimes, but as a HSC Physics marker, we want to see process. Okay, we want to see you plugging numbers into an equation, we want to see you rearranging that equation correctly, and then we want to see you evaluating that equation with correct units, and if it's a vector, a direction. Okay, so B, I would rearrange to 1 times 10 to the minus 4 times 9.8 times 0.05 divided by 15 times 1.7 times 0.02 times 0.06. Okay, now can't do that one in my head. Okay, so we'll go 1 times 10 to the minus 4 times 9.8 times 0.05 divided by 15 times 1.7 times 0.02 times 0.06. So I should end up with 1.6 times 10 to the minus 3 Tesla. Okay, leave it in units of Tesla, don't worry about putting in millitesla. That answer there is fine. It's only asked for magnitude, so we don't need to give a direction. But if we did need to give a direction, we would need to know the direction of current through the coil anyway, which we don't know, so we can't actually answer the direction of the magnetic field.